So what is an LLM? Well, LLM stands for Large Language Model. And this is the thing that powers something like ChatGPT. So after this section, hopefully you'll understand how ChatGPT actually works. But there are a bunch of steps we have to go through. The first step is to understand how you even get a computer that literally only understands numbers to actually understand language. Well, there is a pretty straightforward intuition to understand roughly what's going on. So let's say that you as a human, you take the English dictionary, you just start at the first word. So ace, then amazing, then appreciative, aromatic, all the way to the last word. And there's about 600,000 words in the English dictionary. And you just give them a number. So the first word, ace, has number 1. Second word, amazing, has the number 2. Third word, appreciative, has the number 3, and so forth. So now you can literally take a sentence in English. Let's say, hey, how are you? And you can just look up every word and see what number it has. So for a computer, a sentence like, hey, how are you, is not actually a sentence. It's just a sequence of numbers. So the word hey has, for example, the number 25. The word how has the number 30. The word are has the number 5. And the word you has, for example, the number 75. Now, you may see that these are very small numbers, but that's just to keep it simple. So it's just a lookup table. You have this long list of 600,000 words, a unique number for every word, and you just translate a sentence into a sequence of numbers. So let's go into a bit more detail. How does this actually work? Well, let's start with this super simple model. Let's say that we have this Excel sheet where we have every word in the English dictionary as a row, and then we have every word in the English dictionary as a column. So for every word, we have a percentage for how likely every next word is. So let's say we get the word are. To a computer, that means you get the number 5. And now the job of the language model is to say, what is the most likely next word after the word are? Or more correctly, what is the most likely next number after the number 5, which represents the word are, according to all the words or all the sequences of numbers I've seen on the internet. So you could imagine that as a human, you might give an equal percentage to a lot of words. It could be are you, because maybe the sentence is literally, hey, how are you? But it could be are they? It could be are things, because the sentence may be how are things? It could be are fine, because the sentence may be they are fine. Because you only have one word to guess from, one word of context, it's going to be hard to guess correctly. You literally can't guess correctly. You don't have enough information. But you can do a good guess. So maybe these things like you, they, things, fine, they have the same percentages. But you're going to have words that have a very low chance of being right. Are animals is a very uncommon sentence on the internet, most likely. It happens, it's just uncommon. So again, to a computer, it's not guessing words. What the computer would say is, based on all the text I've seen on the internet, or more correctly, based on all the sequences of numbers that I've seen on the internet, according to this translation from words to numbers, after the number 5, I usually see the number 75, which represents you. Or after the number 5, I usually see the number 42, which represents they. Or after the word 5, I've usually seen the number 97, which represents things. So it's doing something very similar to what you would do as a human. And as a human, you have intuitions about the percentages, and I think it's easy to understand that if a computer could just look at all the statistics over all of Wikipedia and all the internet, it could also have a pretty good idea about the percentages and the statistics about the next word. All right, so this is as far as we get with this one column of 600,000 rows, or 600,000 rows and 600,000 columns. Now, let's say that we get one more word of context. So instead of are, we get how are, which to the computer, again, is the numbers 30 and 5. Well, now the percentages change. For you as a human, when you just had the word are, there were, you, things, they, fine, were equally likely. But when you get two words, how are, all of a sudden, you is probably more likely. Maybe it's 50% likely now. Because it's more common to say, how are you on the internet than how are they, for example. So if you had to guess, you'd probably go with how are you. And it's even more likely to say, how are you or how are they than how are things, perhaps. And if you take something like fine, which was pretty likely when you just had one word, because are fine could happen if you say they are fine. No one says how are fine. So now all of a sudden, the word fine has a very low percentage. Translating this to numbers, what it means is the large language models now has two numbers to guess from, and just like you as a human would guess much better with two words, the large language model, based on all the numbers it's seen on the internet, is going to guess much better with two numbers as well. You can imagine what comes next. What if you had three numbers or three words? So now the context is, hey, how are, or the numbers 25, 35. Now your guess is going to start to get really good. Hey, how are you is now very likely. Let's say it's 70%. Hey, how are they? Maybe even less likely. You might say, how are they? But you seldom say, hey, how are they? Because they are not in front of you. So that might go down to 5%. And something like, hey, how are things? That was a bit less likely than how are they, now shoots up. Because, hey, how are things? Is something you would see on the internet quite often. And then, hey, how are fine? And hey, how are animals? Very low percentage. So the whole point is, the more context you get as a human, the more words you have, the better your guess, the more sure you're going to be about the next word. And it's the exact same thing for a large language model. The more numbers it gets, the numbers represent the word, the better its guess is going to be on the next number. So in a sense, this is all that a large language model does. It just guesses the next word, or more correctly, the next number from previous numbers. And so it's actually a little bit of a misnotion that we call them large language models. They should probably be called large number models or large sequence models, which they are called sometimes. Because it turns out that you can turn words into numbers, but everything are numbers. You can turn pixels into numbers, or actually pixels are numbers. So you can put pixels or an image into these large language models, and based on the previous pixels, the previous pixel numbers, the RGB values, it is going to get very good at guessing the next pixel. You can put audio samples, for example, from someone speaking. Those are just numbers. And if you have those numbers and you train on those numbers, a large language model will get very good at guessing the next sample in an audio sequence. So remember, it's not a language model. It's actually just a number model. And everything in the world can be translated into numbers. So anything that is a sequence, if you have lots of data, these models can learn the statistics about those sequences and correctly guess the next number. So in a sense, now you actually understand what a large language model does. But there is a problem here that you should understand. Why hasn't this happened before if it's so simple? Well, even though it's simple in theory, it's quote-unquote just statistics, just guessing the next number. It turns out that guessing the next numbers for long combinations of context for many words is very computationally intensive. So if we go back to your Excel sheet, where for every word, you have a percentage on how likely every other word in the dictionary is. Now, I said there were about 600,000 words in the English dictionary, but let's just simplify it and just take like the most popular 50,000, because 50,000 is like roughly the size of a vocabulary that a large language model actually uses. So now we made it smaller. You now have 50,000 rows of words, and you have 50,000 columns for every such word. So that's 50,000 times 50,000. So that's actually a pretty big Excel sheet. It's like 2.5 billion cells or something. So pretty unwieldy Excel sheet, but it's still like sort of doable. It's a lot of cells, but it's doable. But this is just with one word. And remember, when you just had one word to guess from, your guess is going to be pretty bad. Now let's say that you get two words to guess from. So now you're going to have 50,000 rows times 50,000 columns, and then times 50,000 again, because you have combinations of two words. So now you have something like 125 trillion cells in your spreadsheet, and it's getting beyond what is solvable. So it turns out, while the theory, as I said, is deceptively simple, the practice is actually very hard. It's just very, very hard to do these statistics in practice. Enter the transformer. So there's this paper that came out from machine learning scientists at Google in 2017 called Attention is All You Need. And it suggested a specific machine learning architecture called the transformer, which is what you see on this image. And don't worry, you don't have to understand this image at all. It's just going to look cool if you say like, oh, I recognize that, it's a transformer. The only thing you really need to understand is that they managed to find a clever way of solving this problem of how do you have a lot of context. Turns out a transformer can handle thousands of words. In fact, it can handle tens of thousands and recently even something like 100,000 words as context just to guess the next word. So think about that. Like 100,000 words. That literally means that the job that you would have as a human is you get to read an entire book and you just hide the last word on the last page. But you have the entire book as context to guess the missing word. And your guess would be amazing, right? You would be almost completely correct in that guess because you would have so much context. Even if that missing word was something very unlikely, let's say that the story ends and then she went to, right? And maybe the correct word is Pluto, but you would know that because you know that the rest of the novel was about space and she was on her way there, right? So you would be able to make even very unlikely but correct guesses because you have context. This is the problem that the transformer machine learning model solves, so this architecture. And the reason the paper is called Attention is All You Need is because the way it solves this is that it allows the model to literally pay attention mathematically to put different weights on different words. It doesn't put the same weight on all the words, so the problem doesn't blow up in the same way as your Excel sheet did. It can pay attention to different words depending on the guess. Now, if you want to know more about this, you can read about it, but the only thing you really need to understand is that the transformer model solves the context problem in a very clever way. And if you want to go into this, don't be afraid. The math isn't that hard. It's actually mostly a bit of linear algebra, a little bit of calculus, but not the hard stuff. This is not quantum mechanics. So if you want to go there, go there. But this is what everyone is talking about. This is what the transformer model is. It simply allowed machines to do these statistics on internet scale. All right, so now we come pretty far. So now we have this thing that is very good at guessing the missing word. So let's take this sentence, for example. My dog's name is Ben. He's a big dog with large paws. Ben likes to play fetch with me. Let's say that the large language model tries to hide the word fetch, right? So it is on the word play, and it's supposed to guess the next word. Well, you can imagine in the model where you just get the word play, the best guess would maybe be play soccer. It's the most common word on the internet. Play basketball, maybe. Play fetch is pretty uncommon. But now that you have context, the language model can say that who is playing? Well, it's Ben. And then it goes even further back and says, my dog's name is Ben. He's a big dog. So now it knows that Ben is a dog. And now all of a sudden, with that context, the most likely next guess probably is fetch, because that's the most common word or number to follow that sequence of numbers. So now we have this attention-based transformer that is very good at guessing the missing word, and it can train itself on the entire corpus of text on the internet. So we're almost there. So now we can generate language. How do you generate language? Well, let's say that we have this sentence, how are the numbers 30 and 5. Now, all you do when this model is trained is you say, what is the most likely next word according to everything you've seen on the internet? Well, it's probably going to say the most likely next word after how are, or the most likely next number after 30 and 5 is you, okay? So then you add the word you. And then you take the text you just generated and you put it back into the model and say, now given this text, how are you? What is the most likely next word? And then the model says, okay, after how are you, I think the most likely next word is I. Okay, so we add that. And then we take the sentence and feed it back into itself again and say, after the sentence, how are you, I, what is the most likely next word? It's probably going to say something like, the most likely next word is am. And then we add that. And now we feed this into itself and ask, what is the most likely next word? It's probably fine. And this is how you build sentences, and you can just keep going forever. So what you do with these language models is you put in some text, some numbers, and then you just ask it to fill out the likely next number, take that, feed it in again, add the most likely next number, take that, feed it in again, forever. This is what is called an autoregressive model, by the way, if you ever hear that word. It just takes the context and tries to guess the most likely or one of the most likely next words. So now we can do something like this. You could, for example, feed in half of a Shakespeare text into the large language model, which to the language model, again, will be a long series of numbers, but it will have seen these numbers on the internet. There's a lot of Shakespeare text on the internet, Shakespeare or Shakespearean text. So it's going to say like, hey, I recognize these numbers. I know what comes next. So if you just take the most likely next numbers again and again, you are going to get something that is either very close or quite literally actually the rest of this Shakespeare play. So that's pretty useful. Now we have this thing that can take a piece of text and complete it with something very likely, often actually, if it existed on the internet, not just very likely, but even the exact same thing. Because if you see a lot of the same Shakespeare play, those exact words of the Shakespeare play are the most likely next numbers, right? Okay. But what about creativity? We just said that ChatGPT doesn't just repeat the things you've seen on the internet. We just said that it can write poems that never existed. It can write new text. So how does that work? Well, we need to go one level deeper to understand this, but bear with me, because we're almost there. Now you need to understand something called temperature. So what we said previously was that we have the words how are, or to the computer the numbers 30 and 5. And we said that we took the most likely next word, which is you. That's if the temperature is 0. Let's imagine that 0 means you take the most likely next word. And then you take the most likely next word after that, which is I, most likely next word after that, which is am, most likely next word after that, which is fine. And so you're going to get this sentence, and you're actually going to get this sentence every time, because these words will always be the most likely. So there's this misunderstanding that large language models are probabilistic, meaning that they give different answers every time, because when you use ChatGPT, you actually do get different answers every time, even for the same query. But in reality, large language models are very much deterministic. If the temperature is 0, if you take the most likely next word, of course, the statistics don't change. You will always get the exact same sentence. What is happening in these large language models is that when you want them to be a little bit creative and not just boring, not just repeat what you already know from the internet, you actually do something different. What you can do is you can pick something that is very likely, but not the most likely. So think of it as, instead of taking the word that is the 100% most likely, which in this case would be you, and it will be you every time, you randomize a little, but around the most likely words. So you're going to pick one of the likely words, but not necessarily the most likely. So you're still going to take a word that is very likely. And that's important, because if you take a word that is very likely, the sentence is still going to make sense grammatically, because the word is likely, and it's still going to make sense semantically, because the word, or number in the case of the machine learning model, is likely. So let's say that we take not the most likely word you, but we take the second most likely, which is they. So now you actually created text that never existed on the internet. The statistics are likely, the sentence is going to make sense, because you're picking something that statistically comes after how are, but is not a copy of what existed on the internet. It is, by definition, something new. And this is called raising the temperature. The more you raise the temperature, the more you sort of randomize around the most likely words. And you can imagine that if you stay very close to the top, it's going to still be quite similar. It's going to be new. It will not have existed on the internet, unless by chance, but it's not a copy of what existed on the internet. It will be novel, but it's going to be very close to what exists on the internet. And you can imagine that the more you raise the temperature, the more you randomize, the further you go from the most likely, the more creative the model is going to get. But if you go too far, it's going to start to pick words that are unlikely. So if you raise the temperature too much, it might just say, how are animals? And so quite literally, if you raise the temperature too much, the model goes from seeming very creative to starting to seem a bit unhinged and insane. And I think it's a very interesting analogy to humans here. It tends to be the fact that the most creative humans are somewhere on the borderline of very creative, and sometimes they just seem crazy. And maybe that's a coincidence, maybe it's not. Maybe they just have a higher temperature than the rest of us. We'll know someday. All right. So now we have a large language model that can not only complete a piece of text with the most likely text, but if you raise the temperature a little bit, it can actually complete the text with something novel that never existed before. So now we're pretty close. This is actually GPT-3, which was about a year and a half ago that came out. That was sort of an autocomplete on steroids. It could take some text and it could complete it very believably. And if you raise the temperature, it could complete it with something that was never written before, right? But it wasn't ChatGPT. For those of you who had access to it, it was quote unquote just an autocomplete on steroids. So a way to think about where we are now and where OpenAI and other companies were about a year and a half ago, this GPT-3 stage, it's sort of it's called a base model. And you can sort of think about it as maybe a kid or sort of an unhinged teenager. It has a lot of knowledge about the world. It can complete text. It can generate text that never existed, but you can't really steer it. You can't really format it. So what you would like to have is something like ChatGPT, where it doesn't just complete sentences, it actually answers your questions. And you would also like to be able to steer it to stay away from certain areas and talk about other areas. Maybe you would like it to not answer questions about how to create a bomb, for example. So how do we get to that last stage? Well, that requires two things. Something called supervised fine-tuning, SFT, and something called reinforcement learning with human feedback. Again, conspiracies against the laity. SFT and RLHF, that's exactly how you get people to stay away from your profession. So let me dig in to what it actually means. Again, it's not very complicated. So let's start with supervised fine-tuning. Now, we said that what we have now is this machine that can take a sequence of numbers and guess the best next numbers. So it's your iPhone autocomplete on steroids. Now you could imagine that if you take a bunch of documents from the internet that happen to be Q&A documents, right? So there's a question and someone else answered it. If you train the model on autocompleting that, it will learn the pattern that every time I saw a question, those types of numbers, question-y type of numbers, there was always an answer. So if you're lucky, even with the base model, if you pose a question to it, and it has seen a lot of question answering dialogues on the internet, it may actually give you an answer just because it's a pretty common numerical or language pattern on the internet. So you could say, Q, what is the width of the earth? And it could say answer some number, right? But it could also just answer with another question, because that's also common on the internet, on all the documents it's seen, that you have question, 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 question. For example, like a math test, and no answers. So it's kind of like, it has some of this knowledge about question and answering, but it's not deterministic. Sometimes you get what you want if you sort of ask it to autocomplete the right structure, sometimes you don't. So what you do with the supervised fine-tuning is, whereas the base model was self-supervised, like it literally trains on all the text on the internet by hiding one word from itself at a time, or one token. And by the way, for those of you who know this, one token is not exactly one word, but for purposes of this presentation, let's say one token is one word, is one number. So the base model trains itself on all of the internet. So trillions of tokens, of text. Now you do something different. You create a small supervised data set. What does supervised mean? Well, it means that unlike the self-supervised, this is supervised by humans. So now you create a bunch of documents that are just the format you want. It's always a question, always followed by an answer. And you create, let's say, pretty small number compared to the internet. Let's say 10,000 of these documents. So now you ask humans to go and create 10,000 documents of questions, answers, questions, answers. And then you take this base model, which train on the entire internet, and you do what is called fine-tuning. You train it a little bit more. You don't start over. It's already trained. You just train it a little bit more only on this data set. That is always a question and answer. And then what happens as an intuition is, you can almost say that the language model keeps all its base knowledge, but then it learns this behavior. So it's going to start answering everything as an answer to a question, just based on this little extra data set at the end. You can almost think of it as it sort of remembers what you did at the end. And if you overrepresented everything should be an answer to a question, it's going to start mimicking that behavior. So now it takes all the world knowledge it has, but it always answers it as an answer to a question. So now we're really close. Now we went from iPhone autocomplete on steroids to a question answering machine, where everything you put in will be formatted and answered as if it was an answer to a question. So now we have an assistant, but this assistant still doesn't have any real behavior or values. It's just going to reflect whatever values and behaviors and statistics are on the internet. Some good, some not good at all. So there is one more missing step, which is when you ask that question of how do I create a cheap bomb out of chemicals from my store? How do you get this thing to not actually answer that question? We just trained it to always answer a question. This is where reinforcement learning with human feedback comes in. So this is yet another step where you use humans. So now we have this language model that you can ask questions and it gives answers. And sometimes it gives answers we like, sometimes it doesn't, both in the content, but also maybe in the formatting. Maybe it answers a question with too much text or too little text. So what we do now is a really clever step, which is we take a bunch of humans again, and we're talking about not millions, but a few thousand. And we take a single question and we ask the language model this question. And then we get a bunch of different answers. Remember, the temperature is not zero, so we don't get the same answer. We raise the temperature a little, and so we're going to get a lot of different answers for the same question. So one question, a bunch of answers. And then you ask these humans to rank the answers. So for this same question, which of these, let's say 100 answers, did you like the most and the least? And you rank them. You give them a score. Let's make it simple. Let's say it's 10 answers, and you as a human are supposed to score them from 10 points, 9, 8, 7, all the way to 1. Best to worst. So now you get a new type of data set, where for the same question, you know what a good answer looks like according to a human, and you know what a bad answer looks like according to a human, and in between. So this is a new type of data set. And now what you do is you take another machine learning model, or actually technically also a language model, and you train it on a little bit of a different task. So what you do is you take the question that you had, and you take one of the answers that you had, you put them in together, and you ask the machine learning model to guess how would a human have scored it. Was this the 10 answer to the question, or was this the 1 answer or the 5-point answer? And then you train it until it gets really good at predicting that this type of answer, a human would have scored 10. This type of answer, the human would have scored 1. So now you build something called a reward model, a model that is good at guessing, based on supervised data from humans, what the human would have thought about this answer. Okay, so now we're almost there. So we have the large language model. We super fine-tune it to always answer as if it was asked the question. And now it produces answers, but it produces answers of varying quality. Now we have this other model, which is a reward model, that can look at an answer and say what a human would have thought about it, if it was good or bad. Now you just take these two models, you hook them together, and you just let it go. This is the reinforcement learning part. Now it can supervise itself again. It takes a question, generates an answer, scores its own answer and said, that was bad, I should do better, I should do this. It scores that answer and said, that was good according to human, I should do more of this. So now it can train itself against the reward model. This is what is called the reinforcement learning. And this is a closed system where you don't need humans, so you can do this millions, tens of millions, hundreds of millions of times until it gets really good at answering, not just in the format that a human wants, but also in the style and literally if you choose the values that a human wants. So I think this is interesting because people ask, like, what does this model think? What are the values? And the truth is, in the base layer, the values of the model are just an average of the entire internet. It is what the internet thinks, good and bad. But the reinforcement learning step is actually what inserts a certain behavior. And that is actually a pretty small group of humans. So that is where a lot of the responsibility lies for how this model behaves. All right. That is ChatGPT. Now you understand how it works. You've gone from back in history all the way to 2023. You understand how these things are passing the Turing test. It wasn't that complicated, was it? At least you can imagine how you as a human would solve these things if you had infinite time and infinite big Excel sheets. So now one question is, why is everyone so surprised? And why did, quote unquote, no one see it coming? Some people claim they did, but most didn't. Even machine learning scientists are very surprised in general about how quickly this happened. And the machine learning models themselves aren't that new. The transformer architecture in 2017 was clearly an innovation, but language models has been around and modeling language has been around for a long time. So what was it that surprised people here, including the experts? Well, it was the scale and speed. So the notion of guessing the next word was not something that was recently invented. People have been trying to do this for a long time. And when the transformer architecture came along, it became easier to do it at scale. But what wasn't obvious was that just doing this simple thing much more would start giving completely new behaviors, what is called emergent behaviors. So you could see these large language models not being very good at certain things, like math, for example. And then without changing the architecture, just by scaling it up, all of a sudden it started getting good at things. And that was surprising, that you would sort of get these emergent capabilities that many people thought would require some new mathematical or architectural innovation. So just that scale alone improved performance was very surprising. The other thing that I think is surprising to most non-machine learning people is this creativity thing. Now, the temperature notion was not surprising to people in machine learning. It's been around forever. But again, the concept was there, but even machine learning people were surprised at that it actually scales to something that looks very much like human creativity. It is very, very much unknown if this is what we do, but certainly the result looks like what we do. So either we got the type of creativity that we have, or we managed to simulate the type of creativity that we have. And that surprised people. And lastly, the thing that was missing was this ability to steer it. The supervised fine-tuning to give it a certain behavior, to be an assistant, and then the reinforcement learning to be able to use it practically. GPT-3 was really cool as an autocomplete, but it was a bit unhinged. And supervised fine-tuning made it the interface workable because it was Q&A machine, but it was still unhinged. And reinforcement learning with human feedback made it practically useful in reality. So those were the unlocks. And I think what is really interesting here isn't that we're not surprised that we finally sort of managed to crack intelligence and how complicated it was. What surprises people is actually the opposite, that we kind of cracked intelligence and it was so simple. It's almost provocatively simple. And I think what this does, so about a year ago, around ChatGPT or GPT-3, these models were often called, quote unquote, just statistical parrots. And that was meant as a derogatory term. Or actually around GPT-2, they were saying like, these are just statistical parrots, meaning that they just parrot back, as I said, statistics from the internet. Like, this isn't real intelligence. It's not very impressive, actually. Maybe useful, but not impressive. But then, as GPT-3 came along, GPT 3.5, ChatGPT, GPT-4, this question of, aren't these things just statistical parrots, turned to, oh crap, what if we are just statistical parrots? And so it really puts a mirror to ourselves. And it gets a lot of people to start thinking about what they are, which I think is very exciting. All right, so we did the first part. We actually went through what a large language model is and how ChatGPT works. And now I think you have as good intuition as most people about what it is that actually happened. So now, hopefully you have at least an intuition for how something like ChatGPT works, why it works the way it does, how it can understand questions and answers, and why when you ask it how to create a bomb, it doesn't actually tell you and rather it says, as a large language model, I'm not going to answer that question. This is the reinforcement learning with human feedback part. All right, so you understand that language is sort of just statistics, because language can be represented as numbers, and maybe they are even to us actually, and numbers are just statistics. But I want to teach you one more thing that I think is really cool. Again, made overly complicated. It's not actually that hard to understand, but once you understand it, your mind is a little bit blown. So you may have heard about something called vectors or vector space or embeddings or codes or distributed representations, all of these fancy words, without necessarily fully understanding what they are. I'm going to explain to you what they are. I'm going again to show you that it's a very straightforward concept, but still very, very cool. So we said that language can be represented as numbers, and you can simply give every word in the dictionary its own number. But it turns out that instead of giving a word just one number, which you can do, you can also do a little bit better than that. So you can take a word and you can represent it. Instead of just saying the word R is the number 54, you can say I'm going to use like 3 numbers or 4 numbers to represent the word R. What do I mean with that? Well, let me show you. Let's take a very simple world. Let's say we live in a universe that only has 3 dimensions in it. Only 3 dimensions. Things are either royaltiness, they are masculinity, or they are femininity. It's a very simplified universe. It only has 3 dimensions to everything. So now in this universe, you can take a word, for example, like king, and you can say, instead of just saying king is the number 29, you can say how much of these dimensions are in the word king. So you can say that the word king has almost 100% royaltiness, so 0.99. Nothing in statistics is 100%. So 1 means 100%, 0 means 0%. So 99 means almost 100% royaltiness, right? Because a king is almost always a royal. But the word king is also very high on masculinity. It's almost 100%. We don't know. Most kings so far have been men historically, we think. And then you have femininity, which is low. Probably not 0. Nothing is ever 0, but low statistically on average. So 0.05. So now, instead of a single number for the word king, you have 3 numbers, which corresponds to some dimensions of how much of something that word is. Now, let's take another word. Let's take queen. So queen is also about 100% royalty, right? A queen is almost always royal. It is very low in masculinity, so let's say 0.05, almost 0, and very high on femininity, 0.98, for example. Let's take another word, woman. So a woman could be royalty, but statistically across the population, pretty low. It's almost 0%. Very low in masculinity and very high on femininity. Let's take a word like princess. So princess is interesting because it is almost always royalty. It's very high on royalty. It is usually not masculine and very high on femininity. All right, so now we have these 4 words described not as single numbers, but as numbers that represent how much they are of some dimension. And in this simple universe, only 3 dimensions: royaltiness, masculinity, and femininity. So now we have these words not described as a single number, but as several numbers. And these numbers actually represent how much of something, of some dimension, are in these words. In this simple universe, we just have these 3 dimensions, how much something is royalty, masculinity, and femininity. But you could easily imagine, as we did before, that instead of just these 3 dimensions, you literally take the entire English dictionary as dimensions. So maybe you could have a dimension that is age, and you could say the word king, if 100% is old age and 0 is young age, a king is maybe 0.7, 70% in terms of age, usually old. Queen, maybe 0.6, a bit younger on average. A woman, literally 0.5, 50%, right in between, whereas a princess would be usually young, so maybe 0.1. And you could just go down the English dictionary, and as a human, you can intuit that you could try to put a percentage on how much of every word in the English dictionary is in every other word of the English dictionary. Does that make sense? So you take the word king, and you take, in the worst case, these 600,000 words, and you try to put a percentage on how much is king royalty, masculinity, femininity, age, car, things that would be 0%. So most of these would actually be 0%. But you can imagine a very long vector. We have a percentage for how much of every word is in every other word. So it would be a vector that is 600,000 numbers. And in reality, that's not how you do it. These models usually have about 1,000 dimensions, and they sort of pick the most useful dimensions. And I'll come back to how it picks them later. But it could be good to know if you're wondering, like, seems unwieldy with 600,000. That's true. You would have about 1,000 dimensions that describe every word and how much of something is in those words. But for purposes of principles from practice again, let's go back to our simple universe where there are only 3 dimensions. So now we have these words that are described in how much they have of these 3 dimensions. Now we can do something really cool. We can actually do mathematics with language because they're represented as numbers. Let me show you. Now, we have our universe with the 3 dimensions. We take a word, we take the vector for that word. So we take king, which was almost 100% royalty, almost 100% masculinity, and almost 0% femininity. And then we simply, literally subtract a man. So we take a king and we subtract a man. Let's do the math here. What happens to the royalty? So we had 99% royalty on the king minus 0.01% royalty on the man. That means 0.98% royalty. We had 99% masculinity in the king minus 99% masculinity in the man. So now we have 0% masculinity. And we had 0.05% femininity minus 0.05% femininity. So we have 0% femininity. So we took a king, we subtracted the man from the king, and we got a new word vector. What word do you think this is? What is it that is 100% royalty, but is genderless? It is royaltiness, pure royaltiness. Okay, so now we got a new word. What happens if we take pure royaltiness and we add a woman? So let's do the math. We have 98% royaltiness plus another 2% royaltiness in the woman. That means we literally get to 100% royaltiness. We had 0% masculinity plus 0.01% masculinity, so almost 0% masculinity. We had 0% femininity plus 99.9% femininity, so almost 100% femininity. So now we have this new word vector, which is almost 100% royalty and almost 100% femininity. What is that? Well, it's a queen. So now all of a sudden, you can take a king, you can subtract a man, you can add a woman, and then you have a queen. So now you're quite literally doing math with words. And this is why vectors are so interesting and useful, because they encode how much they are of something. So this can be really useful, and I'm going to show you how. But first, a question might be, how would you go about doing this in practice? In theory, again, you as a human, you could just sit and guess at these percentages. Actually, we just did. So intuitively, if you can do it, the computer could probably do this. But how would you do it statistically? Well, again, there is the internet. So here's one way of doing it. Let's say that you take the entire internet, or maybe Wikipedia, and for any word you want to learn, in this case, for example, the focus word is learning, you just say how close the other words are to it in a sentence. So for example, in this sentence, an efficient method for learning high-quality distributed vector. You can see that the word for and high are right around the word learning. So that means the computer will give it a high score because it's literally close to the word learning, whereas the word inefficient and distributed vector are further away, so they will get a lower score. So if you just take that simple method of you go through sort of all the documents on the internet and you say, for this word, what are the words that come up really, really close to this word on the internet? They are probably related to this word, so they will get a high percentage. Words that are far away from this word in all the documents on the internet, they get a low percentage. So now, just like with the LLMs, you have a scalable statistical method of learning these statistics and learning these vectors. So now, hopefully, you have an intuition for not just what a word vector is, but also how you could automatically learn word vectors for sort of every word on the internet, just based on how close it is to the other words on the internet in sentences. Okay, so now you kind of know what a vector is, but why is it useful? Well, it turns out that if you go through, for example, all of Wikipedia, and you do this, it's going to turn out that if you think of this in our simple three-dimensional universe, where there are only three dimensions, there's royaltiness, masculinity, and femininity. And you have this vector king, for example, that is almost 1 on royalty, almost 1 on masculinity, and almost 0 on femininity. You can think of that literally as a vector in this simple three-dimensional space that points in a certain direction. Or another way to think about it is that it is in a certain place in that space. So it's going to turn out that words that are similar, if you think about it, that have a lot of the same dimensions, they're actually going to sort of be pointing in the same direction or be close to each other in this vector space, right? So the word king and queen, we just said, they're going to be close to each other because they're both going to be high on that royalty value. They're both going to have a bunch of other words that they have in common or dimensions. And if you can intuit that words can be close to each other or far away from each other in this vector space, then it's pretty intuitive that sentences that are just combinations of words, if you literally take the vector for every word in a sentence and you sum up how much royaltiness and how much masculinity and femininity are in all of these words, you're going to get a sum value for the entire sentence. So now you can also say how close sentences are to each other in this very simplified three-dimensional world. So it turns out that if you look at something like lion is the king of the jungle, that sentence is going to be pretty close in this vector space to the tiger hunts in this forest. And that kind of makes sense to you as a human, I think, because lion and tiger, they're somehow similar. They're both animals, so they will be high on the animal dimension. They're both sort of majestic. Maybe they're high on that majestic royaltiness dimension. Jungle and forest, they should be close, right? The trees in there, they're similar. So it kind of makes sense to you as a human that lion is the king of the jungle is probably close to tiger hunts in this forest. And if you look at the vector dimensions, it will be, because it will score high on the percentages on the same dimensions. Whereas a sentence like everybody loves New York, it's probably going to be further away in this vector space from these sentences. So again, now you have this way of taking a language and not just turning it into a single number, but turn it into several numbers that allows us to understand that certain words or sentences are more or less similar to each other, or what is called close to each other. We thought about it in a simple three-dimensional world, but the real world then would be, if you take every word in the dictionary, 600,000 dimensions, but it doesn't matter. Think of it as 3 dimensions. It's the same concept. Okay, why is it helpful to understand if things are close to each other or far from each other? Let me give you an example that I think will drive this home. Here's another world. This world has 3 other dimensions. It has how much something is rock, how much something is classical, and how much something is EDM, electronic dance music. Again, simple world. There's only rock, classical, or EDM as dimensions in this world. And now we take something that isn't a word, but it's actually a song. Here Comes the Sun by the Beatles, Fur Elise by Beethoven, Levels by Avicii, and Bohemian Rhapsody by Queen. And now we try to give percentages for how much rock, classical, and EDM there is in each of these songs. Let's see if we can agree. So let's start with Here Comes the Sun by the Beatles. It is pretty much a definition of rock, so maybe it's 98% rock. There's not a lot of classical in there. Let's put it close to 0.02. And there's very little EDM. It wasn't even invented then, so 0.01. So now we have a vector for Here Comes the Sun by the Beatles. What about Fur Elise? Well, not a lot of rock in there, so about 0%, 0.01. a lot of classical, sort of the definition of classical, so 99%, and almost no EDM, 0.05. Then Avicii comes along, and there isn't that much rock maybe in levels, let's say 0.02. Not a lot of classical, 0.01, but a lot of EDM, obviously, kind of defined EDM. So let's say 0.999, or 99.9%. And then Bohemian Rhapsody is interesting because it's not just one of the things. I think most of you would agree that Bohemian Rhapsody is a pretty unique song. It has a lot of rock in it, so probably 99% rock, but actually has a lot of classical in it as well, maybe 99% classical. But it doesn't have a lot of EDM, so maybe 0.05. So now you've taken songs, and if you imagine that you as a human, you would sit and take all the songs on Spotify and you would score them on these dimensions. Now it's really useful to understand which of these songs or words, if you think of the song, each song as a word, are close to each other in vector space. So you can say that this user listens to Fy Release. So they may be interested in Bohemian Rhapsody, and they will be close to each other in vector space because they both score high on classical. But they may not be interested in levels because it doesn't overlap at all on any of these dimensions. So levels and Fy Release will be far away from each other in vector space, as will Here Comes the Sun. All those three will be far away from each other. But Bohemian Rhapsody will be quite close to both Fy Release and to Here Comes the Sun because it's high on rock. So this is actually how recommendation systems work, like Spotify. But one question then is, I explained to you how you could learn these vectors for words. You could go through the internet, you could take the text on Wikipedia, and you can say, this word is close to these other words in all the documents on the internet. How would you go about doing this for songs? You almost wish that there would be a lot of documents where songs are close to each other. That's what a playlist is. So Spotify has a few billion of these playlists. And if you think of this playlist as a sentence, you can literally take the song in the middle and say, how close is this song to all the other songs in this playlist? Or if you think about all the playlists as one big document, if they're in the same playlist, they are probably close to each other. So songs are in the same playlist, they would score high relative to each other. So you can see how you could build a vector where you kind of understand how much of every song on Spotify is in every other song on Spotify as a percentage. And now you have a vector representation of every song on Spotify. And because it's a vector and it lives in this multidimensional world, you can do recommendations. So a taste profile on Spotify is actually, if you simplify it a little bit, just all the songs that you listen to and all those dimensions added together. So you get a score for how much classical is there in all the songs you listen to. You sum that up, you divide it by the number of songs, and then you have a classical score for that user. You do the same for rock, the same for EDM, the same for jazz, and now you have a taste profile for that user. And now you understand where that user is in the vector space. And you can say that these two users, they have almost the same vectors, they're close to each other, they have the same music taste. So now, not only do you understand what vectors is and vector space, embeddings, codes, distributed representations, it's all the same thing. It's all what I just showed. There's different names to make it seem harder than it is. But you also understand why it's useful. And you actually happen to accidentally understand how a recommendation system works. All right. So now, you hopefully understand what a large language model is, how ChatGPT works, what a word vector is, and why it's useful.